So can I please ask Mr. Kona to the podium for the first presentation? He will speak on the analysis to identify critical component failure in onshore wind turbine generators. Please, thank you.
I'm Kona, as introduced, and I'll be discussing a study on an analysis to identify critical component failure in onshore wind turbines. So a bit of a company background. Globalic is a company that develops energy projects within Africa and the Americas. So Globalic South African Management Services, the company that I work for, is contracted to manage 3 independent power plants, namely DR Solar Power and Driefontein Solar Power, which is solar PV plants with a generation capacity of 49.4 megawatts. And also Jeffreys Bay Wind Farm, which has a generation capacity of 138 megawatts, and it has 62.3 megawatt wind turbines installed on it. So the study that was performed was based on the real operation data that is acquired from the Jeffreys Bay Wind Farm over a period of 24 months. Oops. A bit of background in terms of where I work and what inspired the study. I work at the Remote Monitoring Center at Globalic. So our key objectives within the organization is to monitor the portfolio of assets within the organization and maximize energy production mainly and provide technical supports to technicians on site. As you can see, a picture in the background shows our Remote Monitoring Center where we essentially, where the SCADA systems are connected essentially to provide technical support to all these sites. Okay, so my presentation will discuss these topics. I'll be discussing the availability and reliability in turbines, benefits of studying reliability and availability in turbines, and the data that I used for this, and the approach, and the key findings, recommendations, and conclusions for that. So simply, a wind turbine is a system that that converts wind energy into electrical energy with modern wind turbines. So reliability, this turbine is made out of many subsystems which are supposed to operate together to ensure that this turbine operates within its design specifications. So reliability is a study of the probability that these wind turbine subsystems are going to operate throughout the turbine's operational life. So there are a few standards around availability. There are IEC standards or terms used in availability. So a simple calculation for availability as represented would be the time in which your turbine is unavailable, and that can be agreed upon differently between the wind turbine owner and the manufacturer on which parameters to use when calculating this. So my main focus is around unavailability of wind turbines due to faults that occur within the wind turbine and that cause it to cease operation, whereas it is in a non-operative state. A bit of an introduction about reliability. So a wind turbine, like any repairable system, is expected to experience changes in failure rates throughout its operational life. So the image on the left shows the expected failure rate throughout the wind turbine's operational life. Whereas in the early life, it expected to experience a decrease in failure, and throughout its middle life, it's expected to experience constant failure and an increase in failure throughout its wearing out life. This is towards the end of the 20-year lifespan. So knowledge of this throughout operations and maintenance activities can be used to optimize maintenance strategies and optimize stock in terms of components not being available when repairing systems within these wind turbines. So another problem I'd like to highlight with simply studying wind turbine availability by not considering the wind turbine components looks at the image on the right, on the bottom right. The scatter plot indicated there is the wind turbines availability throughout the 24-month study period, and this shows that when the wind turbine average availability is average for all the 60 wind turbines considered, you would find that these wind turbines meet their expected availability. But a deeper analysis of this turbine availability indicates that there are a few wind turbines which are lagging or which are outliers from the mean wind turbine population data. So one of the issues I'd like to highlight is the benefits that come from studying a detailed subsystem component failure in wind turbines. So the International Energy Agency tasked a group of experts to perform or to recommend best practices for performing reliability and operations and maintenance activities for wind power plant operators. So what we used for the study are the recommendations that were provided by the agency. So we will discuss this and break them down in terms of how the data available was used to meet the objectives of studying availability and reliability in these wind turbines. So mainly the data group that was used was the SCADA data from the 60 operational wind turbines. This was a reliable data source and one of the only reliable data sources that we could use for the study. Otherwise, the International Energy Agency does make provision for using other data sources for your study. However, for this study, we used mainly equipment data, operational data, and failure data, which is acquired from the SCADA system. Rubric is shown on the right for the approach that you can use for dividing your wind turbine components. Oh yeah, so another thing that you need to keep in mind when doing this is now the wind turbine component, the wind turbine itself needs to be divided. Wind turbine equipment boundaries need to be demarcated within the wind turbine itself so that you can now identify which wind turbines are experiencing increased or decreased failure from the population mean data. ISO standards were followed in demarcating the equipment boundaries, and the wind turbine taxonomy that was then developed is indicated on the bottom left of the screen, and that was the main focus of the study. So critical failure is basically the failure of an equipment that causes the immediate cessation of the ability of the system to perform its required function. So based on the SCADA alarm data that was available, this had to be determined. So the SCADA alarm data is basically split into different categories, which now will, based on the alarm state that is active, you will now be able to identify whether the fault that occurred within the wind turbine is due to component failure, or is it due to environmental conditions, or whatever the reasons may be for the turbine to be in the state it is in. So the states that we focused on based on the IEC standards were the outage, failure due to outage, which are faults which could have been foreseen which could have been foreseen, and these were now used to indicate whether it is failure or not. So a basic analysis of the data that was available, of the alarm data from the SCADA system is indicated on the left, on the top left of the screen, whereas we can see an increased we can see that electrical subsystems or the generator and grid inverter tend to experience higher, have higher alarms configured within them, and then there are other subsystems with lower alarms configured within them. So this will also have to be taken into consideration with the results that are found in the end. Another thing I'd like to highlight is when a failure occurs in a wind turbine, these are the steps that occur when a failure is recognized. So that is from the point when the failure is recognized, and these are all the activities that are performed by operations and maintenance team. And then finally, the fault or failure is then resolved, whereas the turbine can now begin operating. So that is also to measure the effectiveness of the operations and maintenance activities throughout these steps. So after the analysis of our 24-month, after the collection of our 24-month alarm data, these were the results that were solved, that came up. So a basic indication shows that these subsystems here, which are mainly your electrical subsystems, tend to experience higher failure rates, but of shorter durations over there, if you can read. So these alarms are now categorized into the different categories to have a basic understanding of where these alarms lie. So you can see that the yo-yo subsystem mainly experiences failure durations that are longer as compared to your other subsystems, like your generator box, for example. So according to the recommendations that were given by the International Energy Agency, there are different techniques or methods that can be used to perform reliability assessments on oil operations and maintenance activities. What the approach that was chosen for this was a stochastic non-parametric model to study the failure in these wind turbines. So there are other models, however, which are maybe qualitative assessments or statistical and quantitative assessments, but we mainly focused on performing statistical non-parametric assessments for the approach. So this is just a basic representation of how the data was sorted in order to reach the desired objective of analyzing the wind turbine data subsystem failure throughout. And the results, yeah. So this is just a basic representation of how the results look like when you have applied your statistical models within the failure durations. So the image on the right shows the alarms that were triggered by the wind turbine subsystems. So by simply looking at this, we can see that there are a few subsystems which experience higher alarm failure rates throughout the 24-month period, and also wind turbines that experience alarm durations which are higher than the wind turbine population mean. That's also the same thing that's indicated over there. So next we will then do a basic interrogation of one of the scenarios that occurred in one of these wind turbines that were studied. So this diagram here shows wind turbine 36 that was chosen from the wind turbine population. So by doing a further analysis of wind turbine 36 failure data, you realize that the brake subsystem, the controller, and the hub and the hydraulics were one of these subsystems that were experiencing increased failure rates. Okay, there's something that's supposed to be showing there. It's a bit of a problem. But this then highlights, by doing that, you can now identify which alarms or which components linked to these alarms are showing increased failure rates. So the results that came out was that the brake accumulator pressure was low for an increased number of times. That is over there. So it occurred 5 times, which was slightly higher than the wind turbine population mean, or it was an outlier from the wind turbine population mean. And then, yeah, I wish I could show you this value that was there, but you will realize that it is significantly higher than what you would expect it to be within the wind turbine. This was also applied for the other subsystems where the controller indicated that the CAN bus input-output modules were also experiencing increased failure rates and durations for that. So, over there, I think that's a 19, is it? Is it on? That's it. Can you please move that? Okay, this should be a better illustration. So another one that was picked up was from wind turbine 34, where these subsystems are also identified as experiencing increased failure rates. So what it picked up, there was an increased number of manual stops of about 7, and which accounted for 2.5 lost hours within the study period. And this brake accumulator pressure was also low, which occurred 10 times for that duration over there. And yeah, another thing that was also highlighted was the bad pitch calibration in blade C of the wind turbine, which occurred for longer durations than the wind turbine population mean, which is over there, which occurred 12 times for about 88.2 hours. So yeah, this is just a simple illustration of how this data can be used to gain a deeper understanding of the wind turbine component failure. And this was used using simple tools that are available to almost anyone, like in Excel or Excel spreadsheet and so forth. So in conclusion, we can say that wind turbine alarm operational data has the potential to be particularly useful in the identification of critical component failure in wind turbines, as it does serve as a reliable data source for the study. And this is a summary of the alarms that were picked up from the case studies. Yeah, a summary of the case studies. And the plant data also revealed that the mechanical subsystems experience lower failure rate durations as compared to other subsystems. And yeah, in order to perform this data analysis, you need to have an adequate data source that is, an adequate data sample, or enough data sample to perform this data analysis. And yeah, that's it.
Hi, Kona. My name is Maggie.
Yes.
Based on your studies that you conducted, you spoke about different types of failures. However, I want to ask if you have considered the corrective and preventative maintenance for the strategies in the study.
Yeah. Okay. So the main focus.
And secondly,
okay, sorry,
let me finish. Sorry. or does this correlate with the recommendation your recommendation stated on the presentation?
Do they?
I'm asking about the corrective and preventative maintenance.
Yes.
And at the same time, does both of them correlate with the recommendations that you've mentioned on your presentation?
Okay, so the recommendations were
Thank you.
basically the steps that you need to follow in order to do this analysis. So those were the steps or the methodology that was taken in reaching the desired results. And then in terms of your, what did you ask about optimization of your preventative and corrective maintenance measures? Yes. So the objective of this study is now then, based on this data that you find as a wind turbine operator, you can now begin to optimize your maintenance strategies to fit what your wind turbine failure rate is for the wind turbine population. So as maybe, for example, you might find that your motors are failing, and then you can now maybe optimizing your strategies around the maintenance of your motors in your wind turbines, or directly on a specific wind turbine to identify why is this wind turbine, your motor, failing so many times.
Yeah. Thank you so much.
I think on this side, yes.
Kona, I would like to ask, as a company,
yes,
do you have a software that you make your condition monitoring maintenance, or maybe you use just Excel?
Okay, so currently, this information was used based on the failure alarms that we acquired from Jeffreys Bay Wind Farm. So we are currently not responsible for the operations and maintenance activities on the wind turbine systems themselves. So we are only responsible for the operations and maintenance activities on the electrical balance of plant side of the system. And then to answer your question about are we using models to plan this, we are currently in the process of implementing ISO 55000 compliant organization. So this will be built into the organization's strategies in order to reach that. Yeah.
I saw another question. Yes.
All right, thank you. I'll try to make this as simple as possible with you, but I've got two basic questions I want to ask you personally.
Okay.
Are you representing GlobalEC?
Okay, so
are you representing the GlobalEC organization, or?
Okay, that's a bit of a difficult question. Okay,
yeah,
this
know.
study, I did it as part of my BTech studies.
Okay.
So I used the data that I got from the organization. So I think it wouldn't be fair of me to disregard the organization in my presenting my findings.
Okay, let me just ask the question anyway.
Okay.
I won't kill you with this one, but in relation to what your project was about, it was based on the onshore turbine systems, right?
Yes.
And their failure rate. And the question is, based on your research, were the turbines built or constructed within the ocean area or close to the coastal regions, like in the tropical areas? If yes, would you blame the failure as being caused by the climatic conditions of the area where the turbine is, or you would blame that on the harsh conditions of the wind, or on the poor quality material used to build up the turbine itself? I know it's complex, but just try to be,
okay.
If you're not clear about that, I can try to reference for you.
To answer you, I think a wind turbine, like any operational system or machine, it is expected to fail within its operational life. You cannot find a situation where a machine as complex as a wind turbine does not experience failure throughout its operational life. So this is not to say that the operations and maintenance team is doing a bad job on these wind turbines.
Can I redirect the question, just to redirect you?
Reiterate, yes.
Would you say the failure is due to the climatic conditions of the area where the turbine is? Or would you blame that on the material of the turbine itself? I know the technical team is not to blame there.
Okay.
It's on the conditions or the material.
Yeah, It's not on the acclimatic conditions of the wind turbines locations because firstly, I did not consider alarms that were, or faults that were related to environmental conditions. But of course, there are situations where something fails due to environmental conditions, whereas you might have to do maybe root cause analysis to deeper understand why these subsystems are failing or components are failing in that regard.
Okay, another question, Johan?
Hi, Mr. Kona, thank you for the interesting presentation. Just 2 questions. So you only looked at 24 months. Was it the first 24 months of the project or later on in the project timeline? And then what is the progression of failures as time passed? Is there an increase in certain subsystems failing or is there a decrease in some? I don't know.
Okay.
Thank you.
Yeah. To answer you, this study was now, the data used for the study was taken 6 months after the wind turbine was commissioned. So this was basically to avoid any alarms that may have occurred as a result of the wind turbine operations team or operations and maintenance team learning how to operate the wind turbine, getting started into the activities required to maintain this this wind farm. And then, based on the question you asked about the progression of failure, I do not want to present on that today because I think we still need a deeper understanding of the failure within these wind turbines. But from previous experience or from looking at or from a simple analysis perspective, we did notice a decrease in some of the subsystems. Subsystem failures or failure rates of these wind turbines over the 24 months. So this did indicate that this turbine is now within its early life stages, moving into its constant life stages. Yes.
Okay, do we have a last question before we get to our next speaker?
Okay, there's that graph you showed there on your, okay. First of all, there's an expression you started with, and that gave me some kind of curious mind to ask. There's that equation that has some availability equals 1 minus unavailability divided by all that thing. Mm-hmm. I would love to know the inspiration behind that equation, but after the conference. Here's the exact question. This one is based on the graph that you showed in relation to the times during which the damages are most likely to occur.
Yes.
And there was a time that I think was 1 o'clock, another one was 10 minutes after 1. So this one is more like the question I asked before, based on the climatic conditions of the area now. So I think this has to do with the wind or the current. What is this thing? The tide rise. If it's in the ocean, in the coastal or ocean regions, since it's onshore turbine. So this question is like, don't you think that even the choice of the turbine itself, if you want to make it an onshore wind turbine, is not supposed to be actually close to the ocean itself because of the tide and wind rise and wind changes that are most likely to occur during the midday hours, like 1 and 10 minutes past 1, as it showed up on the graph there. Okay. If you can even go to the graph and just answer.
I hope I understand your question.
I know it's like the first one I asked before, hence I said it's like a follow-up.
This one. Are you referring to this or the...
Yeah, basically the question is, don't you think you would suggest that whoever is constructing the turbines should just entirely avoid constructing one by the shore regions or by the coastal regions due to the fact that the climate conditions at those hours tend to be climax or likely to cause more damages on the turbines? Okay. So would you suggest them or advise them not to even construct the turbines due to that regard? Because there's more damages by 1 and 10 minutes past 1 in there, as I could see in the graph. Okay,
to answer you, when a wind turbine project is developed, let me say so, there needs to be wind assessments that are conducted on a certain location. So this would be to understand is it going to be feasible to perform to build a wind wind power plant on a certain location. And of course, this is now taken, building a power plant on a certain location will now consider whether there is enough energy for the organization itself to generate a profit from that. So yeah, having a wind turbine power plant on land is basically dependent on the location of, or the wind resource that's available at the location where you'd like to build your power plant.
Okay, thank you very much. Thank you again for this interesting presentation. And I would like to welcome our next speaker.
I am Konstantinos, and I'm happy to be here with you today. For the next 15 minutes or so, I will be taking you to a journey to countries around the world that have system operators that have introduced requirements about synthetic inertial response, and I will be also showing you the typical performance of state-of-the-art Type 4 wind turbine generators. Please fasten your seatbelts, take your jackets, because it's quite cold where we are going, and let's get started. In order for you to decide whether there is something in my presentation for you, or you'd rather start playing Candy Crush on your smartphone, or even why not meditate while waiting for the next presentation to begin, I wanted to start by showing you a few highlights of what will follow. In my presentation, we'll be focusing on the Nope. Okay, spoilers. In my presentation, we'll be focusing on the synthetic inertial response by state-of-the-art Type 4 wind turbine generators. Regardless, however, if they are doubly fed induction generator machines or of full converter type, state-of-the-art wind turbine generators are well suited to provide a synthetic inertial response. It can be valuable to the effective frequency management of a given power system that experiences high levels of non-synchronous generation, as, for example, the Hydro-Quebec power system in Canada or Ireland's power system. A key performance characteristic is the It's not cooperating. Oops, too hard. Oh, spoilers. A key performance characteristic of the synthetic inertial response is the recovery period, but this can be nowadays controlled, as we will be seeing later. Always too fast. Before I proceed to the main part of my presentation, a few words about Enercon, just in case you haven't heard of us, and so that I can keep my colleagues from the PR department happy. We manufacture, install, and service wind turbines. So far, we have installed almost 47 gigawatts in more than 40 countries around the world, all of it being onshore. Quite impressive, if you ask me. Over the past few years, South Africa has experienced a significant increase in renewable power penetration on its system. Renewable power plants have grown rapidly in number and in size, with more than 6.3 gigawatts awarded since September 2011 in the 5-bid windows under the Renewable Energy Independent Power Procurement Program. Wind, representing almost 53% of the total contracts awarded, and with almost 1.5 gigawatts of installed capacity until the end of 2016, is an anchor technology in the renewables fold in South Africa. According to the Integrated Resource Plan published in 2016, and I believe this is currently under revision, correct me if I'm wrong, and despite the long and sad impasse with Eskom, it is inevitable that the growth trend will continue in the coming years, and I believe we are all here to ensure that this happens. The increasing penetration of renewable generation, combined also with a change in the patterns of demand, will pose new technical and operating challenges for Eskom. This is not because the performance characteristics of state-of-the-art wind turbine generation are not sufficient to support a stable power system operation. And I couldn't stress that enough. I know I might sound repetitive, I've said that last year, but all beliefs die hard. It is because system operators need to, or have not really, not all of them, but some of them have not been used to, and need to adapt their operating policies to suit the new set of characteristics that this generation comes with, mainly attributed to the fact that it's connected to the grid via power electronics. I will be referring to such generation as non-synchronous throughout my presentation. As or quoting the North American Electric Reliability Corporation, new resources may have different operating characteristics, but can be reliably integrated with proper planning, design, and coordination. State-of-the-art wind turbine generation is not synchronous or non-synchronous, in contrast to conventional generating units that equip most conventional fossil-fueled power stations. Modern wind turbine generators do not inherently react to frequency changes by adjusting their active power output. Unless they are fitted with additional controls, their inertia constant can be considered negligible. Consequently, displacing conventional synchronous or conventional power plants with wind power plants effectively leads to a reduction of a given power system's inertia. System inertia is determining how fast the frequency will change, so there be an imbalance between the system load and the system generation. High levels of system inertia stabilize the system frequency and reduce the rate of change of frequency. As such, displacing conventional generating units, synchronous generating units, with non-synchronous ones might lead better, can be sure, to frequency control challenges with steeper rate of change of frequency events and lower frequency nadirs occurring. For this reason, several system operators have started looking into requiring from wind power plants to provide a form of synthetic inertial response for under-frequency events. By doing so, they aim to increase the maximum allowable penetration level and facilitate the more efficient and economical use of wind energy. ESCOM might face, or South Africa might face similar challenges in the not very distant future. Therefore, it would be prudent to draw upon the experiences gathered elsewhere in the world. Although the number of system operators that is currently looking into synthetic inertial response requirements is growing, only a few of them have introduced related requirements so far. First stop in our journey will be Canada and Hydro-Québec, the system operator of the Quebec region. Already, a summary of all related requirements by the system operators we will be visiting will be presented afterwards. Already in 2005, Hydro-Québec has been the first system operator worldwide to require from wind power plants to respond to under-frequency events by increasing their active power output. The introduction of these requirements has been based on planning studies conducted by Hydro-Québec, so that 3.5 gigawatts of wind energy could be reliably integrated by the end of 2015. Notably, Hydro-Québec's power system is not synchronously connected to any neighboring AC system. Therefore, the projected wind installations would have accounted for almost 25% of its summer minimum load, potentially leading to low system inertia. In order to maintain adequate system performance and limit the frequency fall to what would have been experienced in the case of conventional synchronous hydro-generating units, Hydro-Québec imposed the requirement on wind power plants with an installed capacity of 10 megawatts and more and above to have a comparable performance to that of synchronous generating units with an inertia constant of at least 3.5 seconds. Through system studies, using the wind turbine generator simulation models and actual measurements from field tests, Hydro-Québec revised their grid code requirements and introduced more detail and further clarity. This has happened in 2016. Comparison to conventional generating units is no longer made. Second stop, still at Canada, is Ontario and the Independent Electricity System Operator. That's here. Following the example of Hydro-Québec, the Independent Electricity System Operator introduced speed and frequency regulation requirements for wind power plants with an installed capacity of more than 50 megawatts connected to its transmission system. These requirements can be further complemented by project-specific synthetic inertial response requirements at the wind turbine level through the system impact assessment studies that form part of any connection process for the connection process of any project. In 2015, the Independent Electricity System Operator introduced accompanying documentation that, again, as in the case for Hydro-Québec, provides more clarity and more detailed information with respect to the applicable requirement. Third and last stop is at Ireland, whose power system is also not synchronously connected to any other AC system. Given that, the binding target of 40% of electricity annually coming from renewable energy sources by 2020 would mean that Ireland will experience the highest penetration of non-synchronous renewable generation than any other European synchronous system. One of the key findings of the studies performed by the system operators, Sony and EirGrid of the island, in order to facilitate the transition to renewable energy, was that non-synchronous renewable generation could be reliably integrated with penetrations of up to 75%, instantaneous penetrations of up to 75%, if, amongst others, a set of changes would be implemented, amongst which we have the so-called nowadays DS3 system services. Amongst the DS3 system services, we have the fast frequency response, whose aim is to minimize or reduce the rate of change of frequency experienced in the Irish system. The principle of fast frequency response is to require from a wind power plant to respond to frequency drops in the system by immediately injecting active power output. Similarly to the way a synchronous generator would react, really. To further value the capability of some generators to provide further response, the system operators have proposed an increased tariff for generators that could have a faster response, as I have said, that could be doubled for a response time as low as 500 milliseconds. Interestingly, the system operators in Ireland have followed a different approach to their Canadian counterparts. In contrast to compulsory grid code requirements, the system operators in Ireland require or provide financial incentives through system services so that generators can provide an enhanced performance in the 14 key areas as identified by the DS3 system services. This is a preferred approach, we find, because it can stimulate investment in technical capabilities that are beyond and above the minimum grid code requirements, especially when the provision of such services would come at an additional capital or operational expenditure on the part of the generator. As I promised, here is the table that summarizes all the requirements as this can be found in the documentation by the Independent Electricity System Operator, Hydro-Québec and EirGrid and Sony in Ireland. I realize there is a lot of detail in there, and in the interest of time, I'm not going to spend any time on it, but this is included as well in my paper, so feel free to check it and then check with me if you have any questions. If there is one thing to take away from this table, is the fact that different system operators have different requirements. In order to fine-tune the synthetic inertial response requirements, a system operator needs to take into consideration and carefully reflect the wind turbine generator's capabilities, the specifics of the credible contingency events, the dynamics of the power system, and interaction and response of other generators on the system. In response to the synthetic inertial response requirements introduced by Hydro-Quebec, Enercon was one of the very first wind turbine manufacturers to develop and present the inertial emulation feature already in 2009. The inertial emulation controls are implemented at the wind turbine generator level, and with it, wind turbines can emulate the inherent inertial response of synchronous generators. How is this achieved? The system frequency is continuously monitored by the wind turbine generator's control system, and should this drop below a certain trigger level, the wind turbine increases its active power output almost imminently, and for a given period of time. The energy necessary for this increase is coming from the extraction of kinetic energy that is stored in the rotating mass, namely the generator and the blades. It is noteworthy to mention that activation of the inertial emulation feature does not require the wind turbine generator to be curtailed prior to the event. Therefore, it has a negligible impact on the yield of the wind turbine generator. At partial power output, the aerodynamic power cannot be increased. You can only get so much from wind. So extracting kinetic energy from that is stored in the rotating mass will lead to a rotational speed that is no longer at its optimal level. As a result, the wind turbine generator will experience a recovery period whereby the active power output will drop to a level that is below the pre-event level for as long as the rotational speed is below its optimal point. This performance characteristic is a limitation of any wind turbine generator that is not curtailed prior to the event or is not supported by on-site storage. However, through elaborate algorithms, the active power output can be nowadays controlled in such a way that a smooth reacceleration back to its optimal point of the rotational speed can be achieved, as we will be seeing in a while. The following measurements have been obtained at an Enercon E92 wind turbine generator rated at 2.35 megawatts, forming part of a wind power plant in Quebec, in Canada. This has been fitted with a high-frequency measurement instrument complying with, you can read it, Class A according to the IEC 61400-430 standard. The measurements that you are going to see represent an average of simulated events when the wind turbine generator control system was injected with the under frequency signal you can see here. To account for the influence of the operating point on the inertial emulation performance, three graphs are shown here. One at 20, one at 20, one at 50, and one at 100% of the rated capacity of the machine prior to the event, in order as well to demonstrate the flexibility in parameterization of the inertial emulation feature. Two different sets of characteristics are presented. The blue curves, you can see them in each graph, aim to minimize the active power drop during the recovery period by extending the recovery period, whereas the red curves aim to minimize the duration of the recovery period by allowing the active power to drop to quite a bit more than the blue ones. The change in active power output is presented as a percentage of the rated capacity of the machine, and 0 represents the pre-event active power output. All three graphs show that there is an association between shorter recovery periods and a more pronounced active power drop during them. What we should also take into consideration is the influence of the changing wind speed during the under-frequency event. Depending on the wind conditions, the wind turbine generator might reach faster or not even at all the pre-event, like you can see here, the pre-event active power output. Let's examine this in a bit more detail. This graph demonstrates exactly that in more detail, the influence of a rapid change in the wind speed during the under-frequency event and its influence on the depth and the duration of the recovery period. Here the same color is used to, the same color is used to, for the active power output and the wind speed of each event, and two triggered events using exactly the same parameters can result in a totally different performance during the recovery period, exactly because of the rapid change of the wind speed during the recovery period, and despite the fact that, as you can see, both recovery periods started at almost the same active power output. This suggests that it might not be very straightforward to accurately predict the performance during the recovery period, especially during conditions of high wind speed variations. In conclusion, the nature and the time scale of the different challenges with respect to the grid integration of non-synchronous generation vary and depend on the power system in question. Displacing conventional power plants by non-synchronous generation will lead to a reduction of the power system's inertia. In response to this, system operators can introduce either grid code requirements, compulsory grid code requirements, or system services. The introduction, the development of a common and transparent framework that incentivizes the enhanced performance in this area can be key to developing or to facilitating the development of better performing units on the system over time. Regardless, however, of this, if it's a grid code requirement or a system service, what we need is the proper parameterization of the synthetic inertial response. And this is of crucial importance for ensuring that the operational criteria of a given system operator are met. This has to be carefully studied, discussed, and agreed with a concerned system operator. Finally, the benefits of synthetic inertial response across a wide active power range are becoming more recognized around the world. And it is hoped that the increased confidence in the synthetic inertial response performance will lead to a more widespread application and will make it a mainstream functionality like we have today, fault right through all voltage control. Before Valerie hands you over to the next speaker, I would like you all to just pause for a second and just reflect why we are all here. We can all become so consumed in our everyday jobs and tasks, and I do that and I understand that. But what I find is that sometimes we lose sight of what we are trying to achieve, and we forget what matters, and we become sidetracked. Our goal is to fight and reverse climate change, the single biggest global challenge. I don't need to convince you that this is real, because the good thing with science is that it's true, no matter if we believe in it or not. However, however, there are a lot of people out there, and as you might know, some of them are quite powerful, that think that this is not a problem, that think that this is someone else's business, that don't believe in their own in the power of their own actions, and that's wrong, and that's becoming sometimes dangerous. I would urge you, whenever you get the opportunity, to break the silence that allows climate change to go unnoticed in our everyday jobs and lives, please do it. Whenever you get the opportunity to instigate change in someone's mindset about and habits about climate change, please do it, and do it fast, because the world needs all of us.
Thank you so much. I couldn't agree more. Thank you so much for those words that are actually speaking out of my heart, and this is what WindAc stands for also. We want to get knowledge from what is happening in other countries. We have to bring all that knowledge together so we have a fact base on which we can rely on, and that we can argument to turn barriers into climbing walls. Thank you for these wonderful presentations. Do we have questions in the audience? Let's start here with Richard.
Thanks very much for a very informative presentation. Do I understand correctly that part of what you're saying is that the challenge of integrating non-synchronous generation can be placed with the grid operator, or it can be placed with the plant operator, and one of the plant operator's options is this synthetic inertial response. And secondly, with the work that is happening in these latest state-of-the-art turbines, do you have any ballpark estimation of the cost impact of requiring the wind farms to include these kind of features?
Okay, so to answer the first question, I believe that what we need to do is to have a very big discussion and dialogue with the system operators and with the developers, because we realize sometimes including such features might make the system operators quite uneasy and quite not happy with it, whereas the developers could be simply happy if they could have such a feature, and especially if they could receive something for this, if this would be a system service. But at the end of the day, it will be down on the system operators to define the requirements that non-synchronous generation and any generation connected to their system must meet, so that we keep our lights on. And with respect to the second one, again, it would depend on whether the system operator would like to have this as a compulsory requirement or as a financially incentivized system service. There is a cost associated with this feature, but in the past, other functionalities were more expensive than this. And they are nowadays mainstream, and they are nowadays provided free of charge. I can say that.
Okay. Hi. Yes. Thank you, sir. Can I?
Sorry.
No, okay, no problem.
Okay, then, please.
I'm Jenny Rees from Australia. We're also looking at the introduction of a fast frequency response service in our grid. Do you see a need for a standardization of what this service looks like for manufacturers to be able to have standard kinds of products that are offered? Or do you think that this service is something that, because it's very highly tailorable, it will end up being defined differently in different grids because of the different needs of those systems, and that's actually fine and not problematic for manufacturers?
Well, standardizing the requirement might kill innovation. That's for one thing. And I know we have similar discussions currently in the UK, because the system operator, the national grid, is looking into standardizing the frequency response products, amongst others. And one of the discussion items have been about, do we create a market for the synthetic inertial response, or not really synthetic inertial response, but they name it differently. Do create a market for the frequency response services, and then we attach different values to different performance characteristics, doing something faster, doing more, having less of a recovery period, or do we just standardize a product and then just have the developers bid, and the one that is bidding the lowest wins, basically. And this discussion has not really concluded yet with respect to the frequency response services. If you would like to receive my opinion, I think it would really depend on the country. What I would like to see is the flexibility from your side, so that you can request a fast frequency response, but if someone could deliver something closer to what you would be looking for, like something faster, or more active power during the feature, or less recovery period, or less active power drop, then I would like this to be somehow incentivized.
Yanga?
Thank you. So I wanted to ask, on the first country that we traveled to, there was a 3.5 inertia constant. I'm not sure if you said it decreased to the 3.5 or
3.5 seconds.
Yes. I wanted to ask, what is the reason for this? Is it related to the kinetic power that you want to extract from the power operators?
Yes, exactly. So Hydro-Quebec, the power system operator, saw that if they displaced, they rely quite heavily on hydro, and if they displaced conventional synchronous generators driving hydro, then their system might experience a frequency fall if an event would occur. And they said, fine, we'll just need to make the wind turbine generators that will connect have the same impact to the system as the synchronous generator units will have. And according to their studies, they required from wind turbines to have a 3.5 seconds of inertia. The inertia constant can be between 2 and 9, for instance, seconds for synchronous generators.
I think Anna had another question.
Oh, a lot of them.
Oh, a lot of questions, okay.
Yeah.
The last speaker will actually not come, so we have a little bit more time to take questions.
So you can grill me more if you want, okay?
Yeah, let's just... Okay, Anna, do you want to ask a question? Oh, where's the microphone? It's here. Oh, you also had a question, sorry. Please.
To add on to that.
Yeah?
Just to add on to that, are you saying that the inertia constant...
We don't hear you.
I can't hear you.
Sorry. The inertia constant, is it based on today's system?
It was based on the projected installations that would have taken place until 2015, the end of 2015. And they said...
Which means for a longer term study, you then have to do this every single year.
Yeah, because they started planning how their system would look like already 10 years in advance. And that's as well. But you have as well to take into consideration that they have been the very first system operator that have started experience, or at least have started take action about the low synthetic inertia levels.
Have you considered the increase on the failure rate? Is there potentially an increase on the failure rate including this rotating mass?
I can hardly hear you, sir.
Yeah, can you hold your microphone up?
It doesn't work.
Failure rate on the wind
now.
turbine. Oh, cool. The failure rate, have you considered that it may increase the failure rate of the turbine if you include the rotating mass on it?
Well, there is already the rotating mass, and that's the generator and the blades. But this is for type 4 turbines, full frequency converter turbines. This is purely, this is really decoupled from the grid, so it doesn't experience the grid variations, I would say. So what we would do is somehow extract, I'm not going to go into the details because I'm feeling there as well. So then what we would do is extract kinetic energy, so slow down the generator and take power out of the kinetic energy stored in the rotating masses. I hope I have covered you.
Can we take the last question? Because Konstantinos will be here tomorrow, I think, as well, the whole afternoon and tomorrow.
Yes, but I won't be presenting.
You will be?
I won't be presenting, however.
Oh,
so
yes, okay.
you only
Please.
get one chance.
Another.
Okay, it looks like I got lucky then. It's Arne, Flensburg University of Applied Science. You showed on one of the first slides that Hydro-Quebec does not allow you to drop below -5% under the pre-event power.
Yes.
And just, you know, I think I have some numbers in my head. Your power increase was for about 10 seconds. Then your recovery period is for, like, say, 30 to 50 seconds.
Yes.
What does happen if the wind speed drops? How can you ensure that you meet that power demand by Hydro-Quebec, and what are they going to do about it if you violate it?
Well, from what my colleagues have been saying, this requirement can be met with the blue curves that you have seen, and this allows the turbine to limit its active power drop after the activation of the inertial emulation to below 5%. I realize where you're coming from. I know that if the wind speed drops, then the recovery period might take long, exactly as I have shown, might take longer, or the active power drop might be less, and that's a reality that my colleagues have discussed with Hydro-Quebec. I cannot go into more detail because I haven't been included or involved. Better, not included, involved. Yeah.
But they kind of accept that
Yes.
Okay.
Yeah. I mean, they have published quite a few papers, Hydro-Quebec, with respect to synthetic inertial response, and several of them are using the measurement results from Enercon wind turbines. We have already more than 2 gigawatts of wind performing the synthetic inertial emulation feature.
And one really quick question. You also showed full load operation, and it looked like there's a little recovery, or like a little power decrease during the recovery period as well. Why do you need that?
Sorry, I don't...
I think it was where you compared the 3 different operating modes.
Yes.
And there the blue curve looks like it's at about minus, I don't know, 3% or on the rightmost.
Yeah, this is due to the changing wind speeds.
Okay.
So if the aerodynamic power is there, then the wind turbine would recover faster. And to go to where the wind would allow it to go.
Right, thank you very much.
No problem.
Thank you. Then, Konstantinos, thank you so much for your presentation, both informative, inspiring, and we're looking forward to seeing you maybe again next year.
Perhaps 2 Greeks in a row. It's a little strange. Yes, I'm here from the U.S. to hopefully fulfill at least part of the WindAc mission, that is to deliver some long-term experience to this less mature market than the U.S. And I'm here actually speaking on behalf of John Bosch, who's my partner in the company and our principal engineer. So this is one of those cases where we've turned the tables a bit, and an atmospheric scientist is presenting on behalf of an engineer instead of an engineer presenting on behalf of atmospheric science. So we'll see how it goes. Which button do I press here to make this go? The big black one? The green one? Okay, let's see, maybe this one. No, that's the pointer. Okay, let's try this one. Nothing there. Bingo. Holding. Pressing. Ah, there we go. Okay, so the company's name is Arcvar Renewables, and that's a new name. We just went through a merger, my business partner and I, in March, so we just thought a little background on what this means. These are 2 very old consulting firms from the U.S. that came together. VBAR is the company that I originally ran, and it has its origins back in 1978, the very beginnings of the U.S. wind energy business in California. And Chinook Wind is the other company that merged, and it has its roots back to 1990, working on turbine technology and engineering. We're based in Colorado in the United States. Golden's perhaps known to a few of you here for the National Renewable Energy Laboratory, but that's coincidence, turns out. But it's nice to have them close by and get to interact with them a fair bit. Our company's been around a long time, so it's done a lot of things. And so the nature of this quick introduction is that we're old and experienced, and we can help you out, I suppose. But basically, we've worked on 6 of 7 continents. over those 39 years, which I suppose is older than many of the people sitting here in this room. And 25% of our work is international. We did our first assessment of a wind farm back in 1989, and now many of those projects in the United States are actually being repowered. They're cutting the top off and putting up a new nacelle, or replacing 30 turbines with a single large turbine and producing double the energy. Getting a little bit more to experience, we've worked on 40% of the US installed base of wind turbines. That's 35,000 megawatts. And I guess a quick tidbit, it may not be really clear from the current political state in our fine country, but coal has been reduced from 60% of the US electricity supply to under 30% since 2003, with a significant fraction of that caused by wind energy and solar energy. So there is hope despite the current turmoil. Another point there, too, is that despite the proclamations, the rest of us in the US seem to be moving on. Major companies, states, and even utilities are rejecting the recent tendency toward trying to return coal to some prior prominence, simply because it's more expensive to operate. Recent studies have come out that wind and solar are actually less expensive sources of electricity, therefore it's more competitive and better for the people of the United States to have renewables. So that's kind of handy for all of us. With respect to the engineering, our company's worked on over 30 different turbine OEM types. So I don't think we all know that there are 30 still around, but there was a lot of old names back in the 90s and 2000s that are now defunct. We're a relatively small company, despite all that great experience, and almost everybody working for us has about 10 years of experience or more. So we're going to talk about information that's housed in our database, our engineering database, based on pre-construction pro forma information on O&M costs. So what do people think the O&M costs are going to be? We have 73 wind farms from which we've collected information and will present. Then, with respect to actual operating costs, did we really project those things right? We have 58 wind farms in our database related to that. And then also, we're going to be discussing availability, where we have 78 wind farms with almost 500 wind farm years of information. So what's in this database? So with respect to pre-construction estimates, we have a representation of projects from mainly 50-plus megawatts, as you can see in the circle on your left. And among the turbine OEMs, you see 3 of the majors in there, with all due respect to a former speaker. I don't think there is actually an Intercon example here, but in the US, there's a reason for that. So, so Vestas, GE, and Siemens tend to dominate the US totals, and they're well represented here. With respect to the operational database, then, we have project sizes, again, that vary quite a bit, but are mainly 50, 100 to 200, or over 200 megawatts in size. Recognizing the current limits here are 140 megawatts. You may want to concentrate a little bit on the 100 to 200 range. We do have one graphic that's specific to that. Project ages are shown. We have quite a few projects with 10 to 15 years of operating values that we've looked at in mergers and acquisitions and various transactions. The turbine OEMs represented in the operating database are shown there, with, again, GE, Vestas, and Siemens tending to dominate, but some older Mitsubishi and Suzlon projects, along with others. So that's some background. And so here's what the O&M costs that are projected in pro formas, that is pre-construction estimates of how OEM costs are going to change over time. There's plus and minus 1 standard deviation shown there. You can see sort of year 1. The blue line, the average is about 20,000 per megawatt, and it goes up rapidly early and then steadies off. So all these data have been converted to 2017 dollars, and they're based to be clear, this is based on pre-construction estimate information. You can see we have quite a few pro formas that go out now to year 30, and there's a rapid drop-off toward the end there as the expectation is you'll start to reduce maintenance and just move towards the end of time for that wind farm. Get ready to repower, I guess. There's a wide range of projections for these O&M costs, as you noticed. The point that John wanted me to make was that companies that project these things take widely different approaches to how they're going to do it. Some start high and move along at a slow rate of increase. Some start relatively low and increase their O&M costs at a high rate, but you saw how it averaged out there. Some pro formas have low O&M budgets, as I mentioned. Let's see, what am I missing here? Anything? Yes, right. So in the upper right there, the O&M budgets are definitely related to the tenor of the contract you have with the turbine supplier. And I pointed out that there's a discontinuity there at the end where it jumps. Okay, so what are the actual costs of O&M? So we looked at the number of operating years. We broke the data down by the number of operating years. And you can see here the early years, the rates are somewhere near 20,000 per megawatt. 4 to 6 years, not too different in the mean, but definitely increasing with a pretty wide range. If you look at those P25 and P75 ranges represented by the upper and lower ends of the orange box. And if you look at the max and min values, don't we all wish we could get the lower value at that point in operations? I certainly wish some of our clients had that. But then it steadily goes up, and it seems pretty clear that at year 6 things steady out with respect to O&M costs, at least for this database. If we plot the O&M cost over time for 1 to 2 megawatt turbines, this graphic that you see is what we find. There's a fitted curve there that shows 6% growth. You can imagine if you didn't start that line at year 1, the growth rate would be lower. So your assumptions are important in that regard. Let's see. Yeah. So it's a little hard to pick off from that graphic, but we wanted to point out that things do seem to steady out after year 10 or so in the data set, but there are projects there that go through 15 years, but not a whole lot that are going a lot longer than that in this database. So take that with a bit of a grain of salt. For larger megawatt-rated turbines, we find a more rapid increase in the trend for O&M costs. And again, the assumptions again start on whether you're going to start your growth trend in O&M after the first year or not. And we're a little cut off there at the bottom, but I think you can get it. Basically the same conclusion from longer operating history. That is that things tend to level off after year 10. Okay, so by project size, this kind of gets to the size of projects that you all see here, and basically this shows what you might expect, that smaller projects, the cost is spread out over fewer turbines, so the rate for O&M tends to be higher. The O&M costs tend to be higher in the $40,000 to $50,000 range for projects under 50 megawatts inside, but then it more or less steadies out for projects over 50 megawatts inside. So the benefits accrue to those that at least hit that 50 to 75 megawatt range in the US. Whether that applies here exactly or not remains to be seen. So O&M costs by turbine vendor, names shall not be revealed, but you can see there's a wide range here. There's reputable suppliers can clearly benefit a project, and investigating O&M costs in reality for fleets can make a big difference in the long-term success financially of your wind farm. John did want to point out, however, in looking at the data that you can't necessarily take this historical data and predict that the same turbine vendor will have those low values. There are big changes that occur when new turbine models are released across a fleet. So here's the kind of take-home message in effect. That is, we've plotted here data from operating projects relative to the pro forma estimates. And here you can find things match up, at least with the average, rather well through about year 6. But then there seems to be a tendency to underestimate the rate of growth, at least for the majority of cases studied here relative to the actual costs. And escalation, how to handle it exactly after year 10 to 15 remains a little bit of a question. So there's some indication that it's with the growth rates of 6 to 8% in the data that in the pro formas, that those may even need to be increased at times with certain manufacturers, certain technologies, and certain new releases of turbines. It's important to point out, though, that this is in some ways not an apples-to-apples comparison. Actually, it is not an apples-to-apples comparison. The pro formas are more recent and based on recent turbine models, and the data is from old wind farms with different turbine models. So these two, they don't match up, but they're, because it's not apples to apples, we can't say for a given turbine model exactly whether it would follow this basically this operational difference between O&M costs later in project life. We don't know whether that would be maintained for modern turbines that are new pro formas, because they don't exist yet or haven't been operating long enough. So there's plenty of caveats here. I'm going to let you just read those and focus on the lower left, in the little green bracket there. John wanted to make a clear point that in his experience over those many years since 1990, having a very experienced operational manager on site is the single largest factor that determines how your wind farm performs with respect to O&M and O&M costs. So the conclusions are probably self-explanatory since I just walked through them all, but we can talk about the costs in the first bracket there. They tend to range from 20 to 30K per megawatt in the first 5 years. Escalation of O&M costs in that 6 to 8% range, depending on start year, depending on turbine model nameplate. The smaller projects have higher operating costs than larger projects, and the savings diminish above around 50 to 100 megawatts. Reliable turbine models are important, and actual OEM costs from operating projects match projections reasonably well early in project lifetime. Oops, wrong one. So we wanted to communicate how you might use this data. Given the fact that turbine financial modeling is going out 25 to 30 years now, ensure that you've considered this type of information as you move towards those longer lifetime estimates. Plan your operational strategy carefully. That is, if you're going to transition to self-performing your O&M after the period where the OEM is doing that work, do so with great care and make sure you hire a top person to oversee that. It's well worth the money and salary to do so for the long-term performance of your wind farm. And there's a couple other conclusions there, but it is a little difficult to forecast future O&M trends based on this past data. So that's what we have. There's some thank yous there for the team that helped gather all this data and organize it. And I've got John's contact information there. You should definitely talk to the engineer, not the atmospheric scientists, if you have operations and maintenance questions or root cause analysis that you'd like to have done. So thank you for bearing with me as a non-engineer as I present this information.
Thank you very much for your presentation, and I would like to stress that we are very happy to have non-engineers amongst us. It's not only engineers that are here presenting. And do we have questions for Greg? Can you please come to whoever is first? Oh, Shalanda.
Hi, thank you so much for this presentation. It seems to me like this is a very important project. Unless I missed it, and maybe you talked about this, do you have any sense of how closely the cost overruns, essentially, for the projects that are in operation match the contracts? Or, because I know that you're matching them to the current projects, so it's an apples to oranges comparison. Were you able to get access to the contracts for the projects that you had the costs for?
Some of these include both, but we didn't break it out.
Okay.
So it's just missing from the presentation. We can definitely follow up as long as it doesn't give anything away.
Right.
It might be a small number, so there's some risk of releasing information that shouldn't be released.
And then my follow-up question is basically about risk. I'm a lawyer, so I'm wondering how you manage that risk and who you think should be absorbing the risk based on these projections.
Let's see. Who should be absorbing that risk? Should be. No, I guess I would say that the project owner ultimately is the one that's going to have to absorb that risk, especially long term, depending on how you plan your O&M. But as to who should hold the burden for it beyond that, is there a circumstance where you would put that on the turbine manufacturer is the question, or it's a good question. I mean, certainly there are clauses in the contracts that protect from certain failures of components that cause large O&M, and those are reimbursable under the right circumstances with good lawyers. You might find us some battle back on that, but I don't have a great answer for who should. I know traditionally, though, the project owner-operator, once they take over, it goes to them. And then if you follow on with a different, I mean, there are many companies that are offering O&M services now. If you follow on with them, you can definitely put conditions into the contract that protect the project operator. There's no doubt there. Target performance, that's reimbursed.
Thank you. Richard?
Thank you. Do you collect any data on employment, and or do you have any idea whether the employment rate in operation and maintenance increases similarly to the cost?
You're saying, are there more people hired at a given wind farm as this is going up? That's a good. Yeah, I don't know. I do know that in the United States, the single fastest growing job category is wind turbine technician, which is a pretty amazing thing to think about, just like it's also amazing that Vestas is the single larger employer in my home state of Colorado. Who would have thought it in an oil and gas state? But yeah, wind turbine technicians are the fastest growing job category in the U.S., so there's some indication anyway that maybe a combination of a lot of wind farms going in plus increasing O&M requirements are changing the way that technicians are being employed over time, increasing it. If we do, I'm unaware. I can certainly check with John. I don't think, I bet quite a bit of the information we have does say the number of turbine technicians on a site, but it's not something we presented, that's for sure.
If we don't have any other questions, I would say that we go for the last coffee break. Thank you so much again for your presentation and for coming.
Thank you.